Well, here I am back again. As always, kind of thanks for the feedback that you guys give me when you do the exit tickets. I do appreciate reading your ideas and thoughts. It looks like we are going to have a material pickup on Tuesday the 5th for sure. So those of you who said that you were interested, the copies will be available there. They also suggested that they would open it up on Thursday the 7th as well. So if the 5th doesn't work for you for some reason, then the 7th hopefully will. But I'll get you more information about the times. I believe it's going to be open from 9 to 1, the school, but I'll let you know through Classroom. So we are going to continue on with our rational functions, and we're going to look at a couple of things that can happen. So just in a review from yesterday, we had graphs that looked like these top 6 graphs that I drew, and they would change like depending on what was added or subtracted to x. If there was a number in front of x, all of those kinds of things would come into play. And so these are just kind of the basic variation of what they look like. So we're going to look at a couple other things that are going to happen. One of those things that can happen is that you have holes in your graph. And when you have a hole in your graph, it can still look like any one of these graphs that are above. It's just that there is a place where the graph doesn't exist, where it canceled out from the numerator and the denominator. And so you just draw a little hole on the graph. Then there are other situations where we have the same direction around the asymptotes, where on all of these, the ones we did yesterday, on the vertical asymptote, it would go in the opposite direction. So if it went to negative infinity on the left, it would go to positive infinity on the right. And you can kind of see that all the way through. If it goes to positive infinity on the left, it would go to negative infinity on the right. And so we'll see what makes it go in the same direction. And then also we're going to come across some instances where there are no vertical asymptotes at all, and what do those graphs look like? And they come in a couple of different forms. Now obviously I'm not going to touch on every type of rational function that is out there. There are other little things that happen, little swoops and curves and turns and things that happen depending on the values, but these are just some of the things. And if you find the information that we find to graph them, and I'll relist those, number 1 we said factor. Number 2, we are going to find our x-intercept or our zeros. The third thing that we do is we find our y-intercept. Not necessarily in this order, remember. The fourth thing that we're going to look for is our vertical asymptote. Vertical asymptote. Or totes, I should say. There could be multiple. And then the last thing that we're going to look for is our horizontal asymptotes. If they exist, and we'll talk about that too. That could be totes. Okay, if they exist. And so all of these things are going to come into play, and once you find these things, if you put it all together and remember kind of how the rules work, you should be able to sketch a graph no matter what. Even if it doesn't look like one of these, you should be able to put it together, just because again, you can't cross the x-axis unless you have an opening, or even the y-axis for that matter, unless you have an opening, and that comes from your zeros and your x and y intercepts. And your asymptotes give you vertical, that sort of interior behavior, is it rising, is it dropping, and horizontal gives you your end behavior. So you really have everything that you need to get your graph done. So let's go ahead. We'll start this one by factoring. I'm going to pull on the top out an x, so that's x plus 3. On the bottom, I'm going to pull out a negative. That'll leave me with x squared plus 4x plus 3. And then I'm going to factor that bottom one more time. So this is x times x plus 3 over the opposite of, remember that's like a -1 times x plus 1, x plus 3. And so after I did my complete factoring, I noticed that I do have two quantities that are identical in the numerator and in the denominator, and that's that x plus 3. And if they are identical quantities, remember I can't just cancel this x and this x in the x plus 1 because they are not identical quantities. That plus stops me from doing that. They have to be identical. So x plus 3 and x plus 3 are identical. are identical quantities. And when you cancel that out, that's what creates a hole. So we say there is a hole when x plus 3 equals 0. Because that's, if I put whatever makes this equal 0 in here, I'm going to end up with that indeterminate form. Well, I'll get 0 on the top and 0 on the bottom, which is not kind of not undefined and not 0, and it's the indeterminate form. And so that will end up being, that spot will end up being where we have a hole in the graph, a place where it can't exist. And so that's at x equal to -3. And when I do it, I get everything graphed. I draw my graph, I get it all done, and then when I'm done, I go right on to the function at -3, and I'll just draw a little hole on the graph. If you have a pen or a pencil, or if you're using pen, I just draw the hole, sort of connect it right over it. If you have pencil, sometimes you can erase and redraw. But anyway, so we went ahead and factored and found our hole. That's sort of a new thing. Now I'm going to take the rest of this graph and I'm going to do just like I did yesterday, where I'm going to find the zeros. The zeros happen, so the second step is when the numerator equals 0, so x equals 0, and then that's at 0, 0. And then the third step here, this was the first step, factoring. The third step is the y-intercept. That is when I find f of 0. That means I replace all of my x's with 0. And I can do it in the original form, or I can do it in the simplified form. I'm going to choose to do it in the simplified form here. So then I get 0 over -1 times 0 plus 1, which equals 0. And I saw this yesterday. I have only one point. The x-intercept and the y-intercept are the same. If the x-intercept is at the origin, the y-intercept is at the origin as well, because that's where the x and the y axes cross. So my fourth step was to find my vertical asymptotes. That happens when the denominator equals 0. So I set -1 equal to 0, and I set x plus 1 equal to 0. Remember, -1 will never equal 0, so I can ignore that. I know that I don't really have to write this down, but I always like to do it because sometimes there'll be an x that sneaks in down there, and then people forget to set that part equal to 0. And so, or a 2x or something. So I always take each piece. I have 3 different factors in the denominator, so I'm going to account for all of them. And so this is at x equals -1. And then lastly, I'm going to take the limit as x approaches infinity here, and I'll do that with the original function. That's x squared plus 3x over -x squared minus 4x minus 3. Again, you could do it here at this level as well, but I don't know why. I just always like it in the unfactored form. It's easier for me to visualize and see what's going on. And that is -1 as well, so that's the line y equals -1. Okay, so again, I've gotten everything that I need put together, so I'm going to draw my coordinate plane. This is my coordinate plane that I'm drawing, and I'm going to sketch the function on the coordinate plane, not forgetting in the end to put my hole on the function as my last step. So I have a vertical asymptote at -1. I have a horizontal asymptote at -1. I have an opening here to cross the x and the y-intercept at 0. And so now it only makes sense for this to come through and graph in this direction. And now I have to figure out my last piece of this graph. And if I think back at yesterday, I can associate it most with this graph right here. But I do have to remember we're going to have some situations where it goes in the same direction. So then I have to think of other things, like it can't go in the bottom right because then it will fail the vertical line test and it will no longer be a function. It can't go in the upper left because if it does, it would have to cross this axis to approach the asymptotes appropriately, and it can't. cross the axis here. So the only place that it can go is down here in this bottom little corner. And then, like I said, I don't want to forget the hole on the graph. It seems like I can remind. And again, it's another one of those situations where more than half of you will end up forgetting to put the hole on the graph. I don't know how else to remind you or whatever. It just happens because it's something you do at the beginning, and it's the last thing that you have to come back to. And after you do all this work, you're like, oh, I forgot to do that. So my hole, like I said, I just approximate where x is about -3. This was -1, -2, -3-ish. Approximate. Again, this doesn't have to be perfect. And then I just draw a hole right on that graph. So there we go. There's our hole. Now you can have more than one hole in a graph. We might come across some instances where we have multiple holes in a graph. You could have so many holes that almost everything cancels out of your graph except for maybe a line. We'll see that situation. But basically it's the same as yesterday with just a couple little extra things that we have to consider. So let's move on to problem number 2. Go through that same concept, go through that same process, and that is I'm going to start by factoring. So my initial here is nothing to factor on the top, but on the bottom I will take out a 2, that's x squared. Oh, I'll take out a 2x, I'm sorry. Let me redo that, that was bad. X minus 2 over, I'll take out a 2x times x minus 2, and here we go, that's where my a hole is going to end up being. So I say I have a hole when x minus 2 equals 0, and so that's at x equal to 2. Again, I'll revisit that one later on. Now I'll go through the rest of the process. So I'm left with a function that is just 1 over 2x. That's what I'm left with, and that's what I'm going to use to find my x-intercepts, my y-intercepts, my vertical asymptote, horizontal asymptote, etc. So here we are with step 2, 1 equals 0. Well, that's never going to happen, so there are no zeros. Then I will do f of 0, which puts me 1 over 2 times 0, which is undefined. So now I have no y-intercept. Okay, I'm losing everything here. So then my next move is to find my vertical asymptote. That's when the denominator equals 0. So I'll set 2x equal to 0. That's when x is 0. And then I'll find my end behavior, my horizontal asymptote, and that is the limit as x approaches infinity of x minus 2 over 2x squared minus 4x. Take my lead terms. That leaves me with x over 2x, which reduces down to, x over 2x squared, which reduces down to 1 over 2x, bottom heavy, so that limit is 0. So my horizontal asymptote is at y equal to 0. Okay, so got everything I need. Again, I say this a lot. It seems like it's not enough, but if you follow the process, you should get what you need out of this. Okay. So it turns out that my horizontal asymptote and my vertical asymptote are both at x equals 0. I want to try and find a color that I don't know what'll show up. Probably this blue will show up the best on here. They're both right here on the axes. Okay, and it doesn't cross the x-axis, it doesn't cross the y-axis, and so this is one of those instances where I've got to figure out what region this is in. So this is a little bit of a tough one. So what region is it in? So I'll start with, it doesn't really matter where you start, but I'll pick a test point over here. I'm going to just plug in x equals -1. When I do that, I get 1 over -2, and I'm plugging it into this guy right here. So I'm just doing a test point, which is -1/2. So that means at -1, this point is -1/2. Now it can't cross the y-axis, it can't cross the x-axis, so the only thing that this can do is make that little swoop. And then over here on the right hand side, I will do a test point here. If I plug in something like x equals 1, that's on the right hand portion, I get 1 over 2, which means at 1, this is 1/2. And again, same kind of thing. I can't cross the x-axis and I can't cross the y-axis because I didn't have an opening for those to cross. And so the only place that this swoopy portion of the graph can be is in that upper positive region. If this would have come out to be negative as well, I would have drawn it down here in the negative region. It's positive, so it's going to go up there in the top. Now I just have to remember to add the hole in the graph, and so I go back in, and at x equals 2, I approximate this was where I put at about 1, so at 2 it's about here, and then I just put in a little hole, and again, there's my graph. So let's keep on moving here, keep on trucking. We have number 3. It looks like, ooh, that's a little scary. I've got a cubed, but I'm just going to go ahead and factor. I'm going to pick a different color to factor so it doesn't blend in with that stuff above. So I'll go ahead and factor here. I'll pull out on the top a negative 2x squared. And then that leaves me with x minus 4, I believe. And on the bottom, I will pull out an x, and then that leaves me with x squared minus 9. So we will have negative 2x squared times x minus 4 over x times x plus 3, x minus 3. And now there's no plus or minus between here. There is a factor of x on the top and a factor of x on the bottom. So I'll be able to cancel out one of those x's on the top and on the bottom. So this x will go and one of these x's will go, which will leave me with just a negative 2x. So my final function looks like, after I did my canceling, I have negative 2x times x minus 4 on top, and on the bottom I have x plus 3, x minus 3. Which tells me then I have a hole when what I took out was an x when x equals 0. And I don't have to do any solving for that, a hole when x equals 0. I've got some bright lights going on here. Sorry for that. It gets kind of glary. I know I don't have the greatest setup, but I guess it does the job. So I have my hole when x is 0, and now I can go ahead and do that whole procedure where I start to find my my zeros, my y-intercept. So factored, this is what I'm going to be working with. This is the function that's left, so this is what I'm going to be working with. So for 2, I'm going to set the numerator equal to 0, so negative 2x equals 0, and x minus 4 equals 0. So I have a 0 at 0, 0, and a 0 at 4, 0. So 0, 0, and 4, 0. Because I have a 0 at 0, 0, that means probably my y-intercept is also at 0, 0. Not probably, it is. But we'll just do it anyways. Remember, the y-intercept is f of 0, so I put 0 in for all the x's, so I get negative 2 times 0 times times 0 minus 4 over 0 plus 3, 0 minus 3. Because that 0 is in there, that's going to zero out the whole top, but the bottom will be negative 9, which is 0. And so I have a y-intercept at 0, 0 as well. Again, I anticipated that. The fourth thing that I'm going to do is my vertical asymptote. Vertical asymptote is when the denominator is 0, so x plus 3 equals 0, x minus 3 equals 0. Those are my two. So I have 1 at x equals negative 3 and 1 at x equals positive 3. And then I do my horizontal asymptote. And my horizontal asymptote, I'm going to slide that over here just so I have a little more room to write, again, is the limit as x approaches infinity. And I'll go back to the original. So it's negative 2x cubed plus 8x squared over x cubed minus 9x. Bring my lead terms. That leaves me with negative 2x cubed over x cubed, which reduces down to negative 2, so that's y equals negative 2. Okay. So I now have everything that I need. I didn't leave myself a whole lot of room to graph, but we don't need a whole lot of room really. So I'll just start plugging all that stuff in. I have x-intercept, or a 0 at 0, 0, and another one at 4, 0. So those are those 2 points. Those are the places where it can cross through the axis. My y-intercept is at 0, 0, already covered. My vertical asymptote is at negative 3. And I just have to be a little careful. This is at 4, so I'll move positive 3 over here. And then I will do my horizontal asymptote. That's at y equals negative 2, so that's here-ish. And now I can go ahead and sketch my graph in here. So this I know for a fact. It gave me an opening, and I know how it works on either side. This I know for a fact. It has to be in this bottom region because there's no opening for it to graph up here. So it has to be down here. Which means that if this went down on this side, this graph is going to have to go up. If it went down on the left to negative infinity on the left of that vertical asymptote, it will have to go up on the right. And we'll talk about when that's going to change. And then over here, it'll go in the opposite direction because it went up on the right of this vertical asymptote at x equal to 3, so it's going to have to go down on the left in the opposite direction. All right, so now the last thing that I have to do is put the hole in the graph. And what happened was I had a y-intercept and a 0 or an x-intercept that was in the spot where the hole is, and so it's kind of boogered there, but I'll just kind of draw a hole right over the top of that. I made it with black marker just so it sort of stood out. In fact, I could probably do the rest of the graph in that same color so that you can see the hole a little bit better. Okay, so another instance where I had just a regular old graph like we had from yesterday, but this one had a hole in the center of it. Okay, I think 4 is just the same. So 4 is another graph where there's a hole. I'm pretty sure it is. Maybe it's a hole or 2. I can't even remember what I gave you. So I guess let's just jump in. If you want to pause and try it on your own, you can. But otherwise, we're just going to jump right in, and I'm going to start by factoring. So I will factor by pulling out an x. So that gives me x squared plus 5x plus 6. On the bottom, I'll pull out a 3x. That leaves me with x plus 2. So I will continue to factor. I have x times x plus 3 times x plus 2. Two numbers that multiply to be 6, add to be 5, positive 3, positive 2. And then 3x times x plus 2. Oh, okay, now I do remember this. This one is where I have 2 holes. I have a hole at x plus 2, and I have a hole at x. So my holes are at, or when, x equals 0, and when, I should say when, x plus 2 equals 0. So it's at x equals 0 and x equals negative 2. So I have 2 holes in that graph. The other interesting thing that sort of happens on this one is when all is said and done, the only function I have left, f of x, the function that I have left is x plus 3 over 3, which equals 1/3 x plus 1. That's a line. I don't have a denominator. There's not going to be a vertical asymptote. I've canceled everything off, so I have only a line left. All I did was split that 3 between. I put x over 3 and plus 3 over 3, and then I rewrote it as a line. So now, because I'm left with a line, I don't even have to go through that whole process. There's no x in the denominator anymore. I'm left with just a linear function, so I can just graph that line and then put my holes on it. So remember how you graph a line. This goes back to our algebra days. Where do I start? How do I change? I don't know how your algebra teachers taught you, but I start at 1 on the y-axis. That's this. That's my y-intercept. And then this number here is my slope, and so from that y-intercept at 1, I go up 1, right 3. So here I have a point at 1, then I go up 1, right 3-ish. I've got those points enough to make my graph. Doesn't look anything like the ones we've been looking at, and that's just because everything canceled out. So now I just have to put my holes in. I have a hole here at 0, and I have a hole here at 2-ish. Just approximate. Oh, nope, wrong spot. Ooh, ignore that. Pretend that never happened. Make it big. And I meant at -2. So this was down 1 over 3. Oh, so -2 would maybe be right here-ish. Just approximating. Again, it doesn't have to be perfect, but so definitely a different situation than we've seen. Okay, so let's go ahead and move on to our next ones. This is apparently going to be a very long video. I tried to talk faster yesterday just to make it not last so long, but that doesn't always work. But I'm going to start the same. We can jump right in. I can factor 2. This is x squared plus x minus 6. On the bottom I have x minus 3, x minus 3. So 2 times x plus, looks like 3, x minus 2. And over, is that right? No, I think I know what I wanted to happen, but I did not make that happen. Please go back here and change this to plus. Sometimes when I write my problems down, sorry about that, change that to a plus, then that would factor the way I want it to. Okay, sorry about that. Oopsies. So then this is over x minus 3, x minus 3. And this is what I wanted to happen. Something that doesn't cancel out, but where I have that double denominator. That double denominator here is what is going to cause our graph to go the same direction on both sides of the asymptote. So again, I don't have any holes. I can make a comment to myself, no holes on this graph, nothing that canceled out. So I'll go through the rest of the process as I did before to my x-intercepts are when 2 equals 0, when x plus 3 equals 0, and when x minus 2 equals 0. Well, the first situation is never going to happen. So this is -3 and 2, so I have those at -3, 0, and 2, 0. My y-intercept is when I find f of 0. Again, I replace all of my x's with 0, so I have 2 times 0 plus 3 times 0 minus 2 over 0 minus 3, 0 minus 3. That leaves me with 2 times 3 is 6 times -2 is -12 over +9. I can reduce that down, divide the top and the bottom, I get -4/3. My next move is to do the vertical asymptotes. That is when the denominator equals 0, x minus 3 equals 0, and x minus 3 equals 0. That's at x equals 3. Because they both equal 3, that's where the culprit is around that vertical asymptote. If I get a repeating vertical asymptote, I can't draw it twice. What that's going to force to happen is, like usually when you go through one situation where there's an asymptote, it creates a 0, and it'll be positive on one side and negative on the other side. But because this situation is squared, it will force the signs to be the same. I don't know if that makes sense, but it's just sort of a weird situation that happens. And then my horizontal asymptote is the limit as x approaches infinity of the function 2x squared plus 2x minus 12 over x squared minus 6x plus 9. Remember, I made a mistake. Sorry about that. So then I'm just going to look at 2x squared over x squared, reduce it down to 2. So I have a horizontal asymptote at y equals 2. Again, pause and get caught up if you need to. But otherwise, I'm going to put this all together on my graph. I have my x-intercepts at -3 and at +2, approximate about where those are. My y-intercept at -4/3, so that's a little bit more than -1. I have vertical asymptotes at +3, so that's to the right of 2, and that's it. That's the only one I have. Let's see, what else do I have? So +3 minus 2. Okay. And then I have my other guy over here at y equals 2. So that's up here. Okay. Oh, now this one's an interesting one, a little bit different again, but it's okay. We can handle it. So I'll start with what I think or what I know for sure. This part here is sort of giving me a little bit of a I'm not sure. I do know that this is going to have to connect. It has to. It's just kind of a smooth curve here. This doesn't ricochet off of here and go down, so the only natural thing for it to do is to rise up. And then I also know that this has to approach the asymptote. So this one has this little swooping down below that happens. A little bit weird, okay? Now what do I do on the other side over here? Well, it can't cross this axis because there's no opening, so this one has to go up in that upper portion. And this is what I was talking about. This is an instance when I get that double denominator. That's an instance where it's going to head in the same direction on both sides of that asymptote. If this did not happen, this would not happen. Okay, so you have to be aware of that. All right, let's do another one of those. All right, so I am going to start by factoring. I get x plus 2, x minus 2, difference of squares on that one, and then bottom is x plus 1, x plus 1. See what I mean? Here I have that repeat denominator again. That's what's going to cause it to head in the same direction. Nothing cancels out, so I have no holes on this graph as well. And so I can go through and start my process of finding all of the important things that I need. So I have my x-intercept at, or my zeros, when the numerator equals 0, x plus 2 equals 0, and x minus 2 equals 0. So that's at x equals -2 and x equals +2. I have my y-intercept when I do f of 0. That means I replace all the x's with 0, so I get 0 plus 2, 0 minus 2, over 0 plus 1, 0 plus 1. That leaves me with 2 times -2, -4, over 1 times 1, which is 1, or -4. So that's at 0, -4. I have my vertical asymptotes when the denominator equals 0, x plus 1 equals 0, x plus 1 equals 0. That's that repeat thing. So that's at x equals -1, x equals -1. I don't have to write it twice. I just know that around that the graph is going to go in the same direction on each side of those asymptotes because it's a double repeat there. So 5 is my limit as x approaches infinity of the function, and so all I'm really interested in is in the original function the lead terms, x squared plus 2x plus 1. So I will take x squared over x squared, leaves me with 1. Horizontal asymptote, so this was vertical asymptote. This was my horizontal asymptote. And now again I go ahead and I can put this graph together. So I will plot my points. I'm going to write those as points. I should have done this earlier. This is -2, 0, and 2, 0. Not that it's required to do that, and if I were just doing this on my own, I wouldn't, but I just, for your notes, want you to see those. So -2, +2, -4. Then I have a vertical asymptote at -1, and I have a horizontal asymptote at +1. I put that a little bit high, but you get my gist. It doesn't have to be perfect. And so here I know these have to connect, and I know it's got to approach that horizontal asymptote, and it's got to approach the vertical asymptote. I also know that in order for me to, this is going to have to approach this asymptote, and it's not going to ricochet off and go up. It's going to be a smooth thing. There's no other way for it to cross. And because that was at -1 twice, the graph goes in the same direction on both sides. Okay, so now we're down to the last type of problem that we're going to see, and these are a little bit different as well, in that we end up not having a vertical asymptote at all, kind of like the one that we had when we graphed that, oops, I'm throwing stuff on the floor by me here. When I graphed that line, I canceled everything off of the bottom, so I didn't even have a vertical asymptote. And my limit did not approach a number. It didn't approach 0 or a number. It approached positive infinity on one end and negative infinity on the other end because I ended up with a line. This one's not going to end up with a line, but it's not going to have a vertical asymptote. And so it's going to look a little bit different. So on this one, my first goal is to factor, but I can't factor. There's nothing I can do. The top is one quantity by itself, and x squared plus 1 doesn't factor. A difference of squares does factor. X squared plus 1 doesn't factor. There's no combination of two numbers that can multiply to be 1 and add to be 0, because it would be plus 0x in between. That just doesn't work. And so because that is unfactorable, I can just jump right in and start with number 2 and do my zeros. My zeros, again, are when I set the numerator equal to 0. So that's at x equals 3. So I'm going to have a point at 3, 0. I'm going to find my y-intercept. My y-intercept is f of 0. Replace all my x's with 0. So I get 0 minus 3 over 0 squared plus 1. That leaves me with -3 over 1, or -3. So that's 0, -3 as a point. Then I do my vertical asymptote. My vertical asymptote is when I set my denominator equal to 0, x squared plus 1 equals 0. So that means x squared equals -1. When I take the square root of both sides, I get x equals the square root of -1. You see what I mean? That's not possible. I don't have a vertical asymptote. So even if you miss it initially, once you start to try and find it, it will show up for you. Okay, and then lastly, I have my limit, my horizontal asymptote, which is my limit as x approaches infinity of x minus 3 over x squared plus 1. I'm going to take the lead terms, x over x squared. That leaves me with 1 over x, bottom heavy, equals 0. So y equals 0 is my horizontal asymptote. Okay, again, we're going to go ahead and put these together without a vertical asymptote because there isn't one. And then you'll see how things look when we do that. So this is a point at 3, 0, a point at 0, -3. I have a horizontal asymptote at 0. And you might look at this and say, hey, it can't cross an asymptote. But remember, we talked about this yesterday. It can cross a horizontal asymptote. A horizontal asymptote is end behavior. And so this is, again, another one of those situations where it just doesn't seem like there's enough here for me to graph, but really there is. These connect. This is going to have to continue to rise, but eventually it's going to curve back down. Now, I don't know exactly when it's going to curve back down, and all we're going to be doing is a sketch. So it doesn't really matter. I just know that eventually this has to, end behavior tells me this has to approach 0. That's what that is. And so even though it makes sense to come back here, it's not going to ricochet and whirl back up. It's going to cut through that, and then it's going to eventually kind of curve back down. And then on this side, it's going to approach the asymptote as well. So there's another one where we have that sort of little squirrely thing going on. We saw that up here where it's a little squirrely thing going on. But this one, I was forced to do that by the points that were given. This one, I'm forced to do that little squirrely thing because of the horizontal asymptote and the meaning of that, the end behavior. Okay, so a little bit different. Again, we're going to do one more of those. I know I'm getting very long-winded here. I apologize. Tomorrow should go a little bit quicker, but bear with me. One more. So here we go. I'm going to factor. I'm going to take the -3 out. I get x squared minus 4. On the bottom, x squared plus 4 can't be factored. It's just like that previous one. I can't factor it. It's not a difference of squares. It's a sum of squares, and a sum of squares is unfactorable. So this is -3 times x plus 2 times x minus 2 over x squared plus 4. Again, I have no wholes. Nothing can be canceled. So I'll go ahead and I'll start finding all those other little pieces that I need. I'll find my zeros by setting the numerator equal to 0. So I have it at x equal -2, x equals +2, so that's -2, 0, and +2, 0. Then I have my y-intercept by doing f of 0, replacing again all of my x's with 0. So I have -3 times 0 plus 2 times 0 minus 2 over 0 squared plus 4. That leaves me with -3 times 2 is -6 times -2 is 12 over 4 or 3. So that's the 0.03. Then I'll do my vertical asymptotes, which we already said don't exist. X squared plus 4 equals 0. That means x squared equals -4. So x equals the square root of -4. Square root of -4, that's pretty ugly looking, which doesn't exist, so I don't have that. And then lastly, so there are no vertical asymptotes. And then lastly, I do my horizontal asymptote by doing the limit as x approaches infinity. And this one would be -3x squared plus 12 over x squared plus 4. That leaves me -3x squared over x squared, or -3 when I do my limit. Neutral situation, so y equals -3. Get my graph ready to sketch. Let's see if we can get this done before 45 minutes. It's less than 45 minutes. Let's see if we can do it. I'm going to grab, I haven't used this color in a while. So we will put on all of our pieces, -2, +2, +3. Vertical or horizontal asymptote, no vertical asymptote. These have to connect. What has to happen here? It's got to approach that end behavior and approach that end behavior. So last situation that we have. All right, so just sort of funky things that can kind of happen in your homework. So give a few of these a try on your homework tonight. And as always, if you have any questions, please just let me know. Good luck and have a great day. Bye.